Hello everyone, this is Yasmeen Abdrabou from the University of Pfeuffer, Munich, and I'll be presenting our ETRA short paper GazeLockPatterns, comparing authentication using gaze and touch for entering lock patterns. This work is in collaboration with the University of Glasgow. Graphical passwords such as lock patterns are a popular means of authentication, especially among Android users. In lock patterns, users authenticate by entering a pattern that connects up to 9 digits on a 3x3 grid. Lock patterns that are entered via touch, in short as touch lock patterns, have been extensively studied in literature. This resulted in an understanding of how strong the touch lock patterns users created are and also their common pitfalls and areas of improvement. Previous work analyzed passwords created by users of Android touch lock patterns in the wild. For example, Harbach and colleagues conducted a month-long field study in which they logged smartphone locking events. Almost half of the participants had been using touch lock patterns. They found that the average pattern length is 5.9 cells, and only few participants made the strokes invisible. They also found that the authentication time increased on average by 147 milliseconds for each additional cell in the pattern. In addition, another group of researchers analyzed the usability of patterns, and they showed that users are biased in their choices. For example, users are biased towards starting their patterns from the top left corner. Also, another group of researchers have studied the influence of pattern length, line visibility, number of night moves, number of overlaps, and number of intersections on the pattern's observation resistance. They found that the line visibility and length are the most important security factors in addition to the pattern complexity. Literature also showed that users often select patterns that are short and constitute simple strokes. Finally, the research done by Logan and colleagues showed that the age, gender, and experience in IT significantly influenced the strength and length of the chosen patterns. The aforementioned work helped to shape the user-centered security community's understanding of the touch lock patterns usability, and also the way how people use them influence security.
At the same time, advances in gaze estimation accuracy and eye tracking hardware led to gaze gaining popularity for authentication as a more natural and secure modality for entering passwords. Gaze offers usability advantages over traditional modalities such as touch and pointing, and its subtleness makes it more secure against observation attacks. A recent survey on eye gaze for security and privacy applications showed that gaze is promising for password entry. In addition to its usability benefits, gaze is subtle and hard to observe and can be a powerful means to add a biometric as a layer on top of gaze-based passwords. And as an example, gaze can be used to enter the lock patterns seen in the previous slides. Although gaze was employed for password entry and showed promising results for entering graphical passwords, there's a gap in understanding how users create lock patterns using gaze. For example, do users create stronger lock patterns when using gaze than touch, or do they make the same mistakes done via touch lock patterns, making them more vulnerable? For example, the majority of users create touch lock patterns starting on the top left corner, making them more predictable. This knowledge is important to understand whether adapting lock patterns for gaze authentication is a meaningful approach or not. And hence, we implemented a version of the touch lock patterns that employ gaze for drawing strokes between digits on a 3x3 grid. The system is based on an existing application and was implemented in C#. We used a radius of 34 pixels for the interface cells. The pad was centered on the middle of the screen, and the gaze trace feature of Toby was enabled during the gaze condition. For the apparatus, we used a Toby 4C eye tracker along with Microsoft Surface Pro. We invited 40 participants to our study. Their age varied between 20 to 55, with 15 females, 1 left-handed participant, 2 participants with contact lenses, and 14 with glasses. We implemented a between-subject study design where half of the participants did the touch condition and the other half did the gaze condition, which shows 3 different security level scenarios inspired from the literature. The participants were asked to create patterns for different scenarios, such as unlocking smartphone, creating an account for online shopping, and finally creating a new profile for online banking. And as for our study procedure, when the participants arrived to our lab, they were asked to sign in the consent and demographics form. Then we introduced the study aim and we calibrated the eye tracker. Participants were asked to generate a pattern and then re-enter it as a confirmation. The situations were explained one at a time, and those steps were repeated for each condition. For our study results, we studied the effect of the situation and modality on different factors. Here we can see the results of the pattern length between gaze and touch modalities. On average, the length in both modalities is similar, 6.4 and 6.8 characters. We did not find any statistical significance between the two modalities. However, the smartphone scenario length had significantly shorter length than the bank situation. Moving on to the number of intersections in the patterns. Intersections mean strokes which cross already drawn strokes, as seen here in the figure. Users tend to include more intersections when using gaze than touch. The analysis didn't reveal any significant difference between both modalities. Situation comparison shows significantly less intersections with smartphone situation than bank context. A reason can be that drawing intersecting patterns using gaze is much easier than using touch.
Moving on to the number of overlaps in the patterns.
Overlaps means crossing over an already activated cell. No significant difference were found for the modality between gaze and touch, and neither for the situation. We also analyzed the number of night moves participants did in the patterns. Night move specifies the connection of two distant cells that are not directly neighbored, as seen here in the figure. We did not find any statistical significant effect of the modality on the number of night moves in the patterns, and neither did the situation. However, it was noticed that users tend to make more night moves in the online banking situations. In literature, researchers also use observation risk as a measure for pattern analysis. Observation risk is a function of number of the cells, night moves, overlaps, and intersections that outputs a higher number with higher risk. In our analysis, we discarded the parameter visibility of the strokes, as the strokes were always visible in both conditions. We found that gaze has a slightly higher mean observation risk than touch, although no significant differences were found between the modalities. The post-hoc analysis showed that the smartphone context resulted in significantly higher vulnerability than the bank context, indicating that the touch patterns are slightly more secure to observation attacks. However, the nature of gaze input implies that it's robust to observation attacks, indicating that in the future the observation risk equation should be refined. After the experiment, participants were asked to rate the memorability of the created patterns. Here in the table, it shows the participants created similar patterns for both modalities. Analysis didn't reveal any significant difference between gaze and touch. However, as expected, post-hoc tests showed that smartphone patterns are significantly more memorable than the bank ones. We also asked participants to rate the perceived pattern strength from their perspective after creating it. We did not find any statistical difference between the strength of the patterns between gaze and touch. We found minor differences for the three scenarios between gaze and touch modalities, and we found significant differences between the scenarios, showing that the bank patterns were perceived significantly stronger than the smartphone patterns. As done in the literature, we also analyzed the start and end position of the patterns for both modalities. We found that the majority of users tend to start their patterns from the top left corner while using gaze. However, for touch, 32% of the patterns started from the top left corner and 28% of the patterns started from the bottom left corner. For the pattern end position, while using gaze, the majority of users tend to end their patterns with the right down position. However, for the touch end position, 26% of the users ended their pattern with the right down position, and 23% ended their pattern with the top right point. Which means that in general, participants are more aware now with the observation attacks, and they started to change their start and end position of their patterns. Last but not least, for participants whom entered their patterns via touch, we also tracked their gaze position. We aim to study the correlation between what the user is entering via touch and what they are actually looking at. And since authentication and calibration are both secondary tasks in the user's way to achieve their goal, for example, writing a message, calibration is a tedious task, and conducting the calibration implicitly can improve usability. We investigated whether the gaze data collected during touch authentication can be used to calibrate the eye tracker. The idea is that if the user's touch pattern matches their gaze point, we could draw mappings between eye movements and positions on the screen and use this data to calibrate the eye tracker. We plotted the gaze path while entering patterns as seen here in the figure, and we found that users tend to look at the digits they are selecting when entering a touch lock pattern. We also calculated the visual angle of the gaze path for each point on the UI grid by calculating the distance between the center of the UI element and the user's gaze at the moment the finger enters the digit. We found that gaze is close to the digits at the top left corner, for example 0, 1, and 3, as seen here in the graph, and it's further away at the bottom right corner digits, for example 5, 7, and 8. We then analyzed the gaze path with respect to the digit position in the patterns by calculating the distance between the gaze at the moment the finger enters the digit and the center digit position. We found that as the pattern length increases, the gaze data becomes more accurate from 3 angles to 2 angles as seen here in the figure. A reason for that can be, as with longer patterns, difficulty increases, and users visually carefully inspect their touch. Thus, longer patterns can lead to more precise calibration data. To conclude, in our work, we investigated the difference between how users created touch and gaze patterns for authentication. We conducted a between subjects evaluation where we asked participants to create 3 patterns for 3 different scenarios. In our analysis, we did not find any significant differences between gaze and touch when used for unlock patterns. We found that users tend to use similar strategies, like length and overlaps, while using the same interface with different modalities. We also found that gaze is similar to touch while doing patterns, hence it can be integrated to existing systems with no additional changes in the interface. Finally, when using touch lock patterns, the user's gaze is within 2 degrees of visual angle from the touch point. This suggests that future systems could integrate calibration into authentication. Thank you so much for your attention. This was Yasmeen Abdrabou.